Hi everyone. In today's lesson, we're going to take a look at an application of implicit differentiation. And this section is called related rates. And they are word problems. So of course your first step should be to read the problem to gather all of your important information. In some cases you may want to make a diagram to model the situation because pictures can help. Label anything that you're given on the diagram, or it's always a good idea in calculus to make a list of all of your given information. We want to write an equation whose rates of change are either given or it's the rate of change that we're trying to solve for. For number 4, it says find the derivative implicitly with respect to time t, and I'll talk a little bit more about that in a minute. Okay, so there's our implicit differentiation piece. Then we're going to substitute everything that's known to us into the derivative, and then we're going to solve for, hopefully, the one remaining unknown. Okay. Okay, so first of all, before we get into any of the applications, we want to differentiate each of these equations with respect to t, time. So what we're looking at when we're discussing related rates is how quantities change with respect to time. So for instance, that first equation hopefully looks familiar to you. P equals 2L plus 2W. That's the equation for the perimeter of a rectangle. If we want to differentiate with respect to time, it would look like this. So the derivative of P over dt. So you're taking the derivative of perimeter with respect to time. And then that would be equal to 2 dl dt plus 2 dw dt. So it's the derivative of each of those particular variables with respect to time. And number 2, you see a simple formula, area of a circle, and this is going to be used in your homework tonight. If we want to take the derivative of area with respect to time, that would be dA dt. On the right-hand side, remember that pi is a number, so we're taking the derivative of pi r squared. So we're going to bring that exponent out in front, so it'll be 2 pi r to the first now, dr dt. Or you can leave out that exponent of 1 and just say dA dt, the derivative of the area with respect to time, equals 2 pi r dr dt. And finally, the last one, we have an area formula. Area equals length times width, area of a rectangle. It is a product here. All right, so we would take the derivative of the area with respect to time. And now we're going to take the derivative of length. So it would be dl dt. But we would not be taking the derivative of w. So the w, dl dt, plus, now we're not going to take the derivative of the length, but now we're taking the derivative of the width, so the dw dt. So again, I'm using the product rule. I took the derivative of the first and kept that second variable the same, and then I did the opposite. Okay, so now the actual problems. It says in number 4, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius of the balloon at the moment when the radius is 2 feet long. I'm going to highlight in red what we're looking for, the rate of change of the radius of the balloon at the moment when the radius is 2 feet long. Okay, so lots of given information in here. We're working with a sphere, and you can draw one if you want. It's not required, of course. And a sphere has only one dimension to consider, and that is the radius. All right, so if I make a list of our given information, well, first of all, I see this very last piece of the last sentence says the radius is 2 feet long. Right, so we're looking for the rate of change of the radius when a particular moment in time is exactly 2 feet long. So we're being asked to find the rate of change of the radius with respect to time. So we're asked to find dr dt. The other thing that we know, however, is the change in volume, and that comes right up here. It says air is being pumped into the spherical balloon at a rate of 4.5 cubic feet per minute. So cubic feet per minute, that's a change in volume. So we can say the rate of change of the volume with respect to time, or dV dt, is equal to 4.5 cubic feet per minute. Okay, so that's all of our given information. You're also going to need to know the formula for volume of a sphere. The volume of a sphere, in case you don't remember from a previous math course, is 4/3 pi r cubed. Okay, in the end, I want you to round your answer to 4 decimal places. Okay, so start by taking the derivative of both sides with respect to time. So on the left we have dv dt. On the right we have 4/3, and we're going to be multiplying by that exponent of 3. We have our pi. We reduce that exponent by 1, so we have r squared, and we have dr dt. Okay, it's a matter of plugging in everything you know. So we know dv dt. Right here. We know r in this particular moment in time is 2, and then we're going to be solving for dr dt, So dv dt, I'm going to clean this up first before we plug everything in. And then to do that, 4/3 times 3 gives us 4 pi r squared dr dt. Okay, now plug in what you know. The rate of change of the volume with respect to time, or dV dt, is 4.5. We have 4 times pi. We're looking at the moment in time when the radius is 2, so plug 2 in for r, and we're going to square it. And then we're solving for dr dt. So simplify that right-hand side, and we have 4.5 is equal to 16 pi, because 2 squared will give us 4, times the 4 pi that's already there. So we have 16 pi dr dt. And then to completely solve for dr dt, we want to take and divide both sides by 16 pi. So you're going to take 4.5 and divide it by 16 pi. Don't forget to put that into parentheses when you put it in the calculator. And when you divide that out, round it to 4 decimal places, it should come out to be 0.0895. And this is the rate of change of the length of the radius. The radius is going to be measured in feet, and it's per minute. All right, so that's it for our first one. In our second example, it says the surface area of a cube is expanding at a rate of 120 square inches per second. Find the rate that the length of the cube is changing when it is 2 inches long. Then find the rate of change for the volume of the cube at the same moment in time. So this is a 2-part question essentially. We start with the surface area of a cube, and it's expanding at a rate of 120 square inches per second. So kind of an unrealistic problem when you think about a cube expanding this quickly. All right, so what I know so far is that surface area of a cube, well, we have to write a little formula for that. So just a refresher, that surface area is the area of all of the surfaces of your cube. So if we call that the length, the width, and the height of the cube are all the same. So the surface area, there are 6 sides, and each side has an area equal to L squared, or the length squared. Okay, so we've got a formula for our surface area now. All right, so it tells us that the surface area is changing at a rate of 120 square inches per second. So d SA dt. The rate of change of the surface area with respect to time is increasing, so it's positive 120 inches squared per second. Okay, so it says find the rate that the length of the cube is changing. So we want to find dl dt, find the rate of change for the length of the cube with respect to time. And we want to find dl dt when the length is equal to 2 inches. Okay, so length equals 2 inches is a given. The rate of change of the surface area with respect to time is a given. The surface area formula is a given, although we had to kind of figure that out. All right, so the first thing that we're going to find is that dl dt, and then we're going to follow it up with a second problem, essentially, where we're going to find the rate of change for the volume of the cube. So we're going to find dv dt. Okay, obviously we can't find both of these at the same time, so we're going to work with surface area first. Okay, so start with your surface area formula. Surface area is equal to 6L squared, and then take your derivative with respect to time. So it'll be dSA dt, so that's the rate of change of the surface area with respect to time. It equals 6 times 2 times L dl dt, and that's just the derivative of the right-hand side of this equation. Simplify it, so dSA dt equals 12L dl dt, and then plug in what you know. So we know the rate of change of our surface area. That's going to be 120, so let's plug that in. That's equal to 12. We also know L. We're looking at that particular moment in time when the length of the side is 2 inches. So we're going to put 2 in for L. And then we're going to solve this for dl dt. Okay, so we have 120 equals 24 dl dt. And then you want to take and divide both sides by 24. All right, so 120 divided by 24 is going to give us 5, and it's going to be in inches per second. Let's see if I can move this up just a little bit. Okay, now we have to keep this in mind, keep those units in mind. So length would be a linear measurement, that's why it's just inches, and our unit of time is seconds. All right, now for volume. The volume of a cube is length times width times height, and all of those dimensions are the same in a cube, so the volume of the cube is the length cubed, or you can say it's the edge cubed. All right, take the derivative, because now we're going to find dv dt. So we have dv dt, the rate of change of the volume with respect to time, equals 3L squared dl dt. All right, so remember, over here, we solved for dl dt. We're still looking at the moment in time when the length is 2 inches. So we're ready to plug those numbers in and find our dv dt, our rate of change of the volume. So we've got 3, and we're going to plug in 2 for the length, so 2 squared, and then dl dt, that was 5. So when you simplify that, we're going to take 3 times 4 times 5, and we come out with a rate of 60, and it's going to be inches cubed per second. So just try to imagine that every second the volume of this cube is expanding by 60 cubic inches, so it's quite a bit, expanding quite quickly. Okay, on to the next type of problem. You're going to notice that our typical related rates questions are going to fall into some very distinct categories. Our next problem is what I refer to as a Pythagorean theorem question, or a right triangle problem. It says a 15-foot ladder is resting against a wall. We're going to draw a little picture. So we've got the wall over here. We're going to assume that it's perpendicular to the ground, and then we have our ladder. And our ladder is fixed to a length of 15 feet. Alright, it says the bottom is initially 10 feet away from the base of the wall and is being pushed towards the wall at a rate of 3 inches per second. So initially this distance is 10 feet, but the ladder is being pushed towards the wall at 3 inches per second. Alright, it says how fast is the ladder moving up the wall 12 seconds later? Okay, after 12 seconds, we have to figure out where the ladder is. Because if that ladder is being pushed towards the base of the wall at a rate of 3 inches per second, the ladder is going to end up looking something like this. Meaning it's going to be closer to the wall, and it's also going to reach a point higher up on the wall. So we want to find this new distance right here. Well, 3 inches per second for 12 seconds would be equal to 36 inches. And 36 inches is equal to 3 feet. So that ladder has moved a distance of 3 feet. So we can say for sure that after a time of 12 seconds, this distance is now 7 feet. All right, so we're going to consider that our x value. Y will be the distance as it's measured along the wall. So again, it's a Pythagorean theorem question where we can say x squared plus y squared is equal to our ladder squared, 15 squared. So I initially put it in there with x and y because those two things are going to be changing. All right, we know that x after 12 seconds is 7 feet. So we're going to have 7 squared plus y squared equals 15 squared. All right, so let's do some math. 7 squared is 49 plus y squared is equal to 225, and take and subtract 49 from both sides gives us 176. So if we take the square root of 176, it doesn't work out so nicely, so we are going to keep it as the square root of 176. Okay, so don't approximate at this point. Alright, so hold on to that idea. Alright, what we're being asked to find is how fast the ladder is moving up the wall. Okay, so we're essentially being asked to find dy dt, the rate of change of the the wall side with respect to time. How fast is that ladder moving up the wall? So we want to find the rate of change of y in our diagram. So if you go back and you take your Pythagorean equation, x squared plus y squared equals, let's say, 225 or 15 squared, either one, and we take the derivative, we'd have 2x dx dt plus 2y dy dt is equal to 0. Let me just fix that. And that's because the derivative of a constant is 0. Okay. Divide everything by 2 just to make it simpler, and we get x dx dt plus y dy dt equals 0. And you can plug in what you know. We know that x, that distance from the base of the ladder to the bottom of the wall, 12 seconds later would be 7 feet. All right, we know the rate of change of the ladder, and here's where it's a little funky, okay? So dx dt is equal to 3 inches per second, but it's going to be negative because the distance is shrinking, okay? But we want to have the same unit of measure, so 3 inches is equal to 1/4 of a foot. So that distance, the length of this side of our triangle, that's our x value, that's changing by a rate of negative 1/4 of a foot per second, okay? So we had to make our units match. It's got to be negative because that distance is shrinking. So to that we're going to add y dy dt. So y we solved for over here, and it's equal to the square root of 176, and then we have dy dt. Okay, all we have left to do is solve for dy dt. So it'd be negative 7/4 plus the square root of 176 dy dt equals 0. So we have 100 and the square root of 176 dy dt is equal to 7/4. And to solve for dy dt, take 7/4 and divide it by the square root of 176. Okay, be sure to use parentheses and be careful when you're typing it into your calculator. So to 4 decimal places, it works out to be 0.1319, and our unit of measure will be feet per second. Okay, our last example for this video is another cube problem. So it says a cube is expanding at a rate of 6 cubic meters every minute. So it's a really big cube and it's expanding really quickly. It says find the rate of change of the length this time when the volume is 64 cubic meters. Okay, so for this one, we don't have to worry about surface area at all. We're just going to be taking a look at our cube and its volume. So remember, volume was length times width times height, where volume is equal to L cubed. What we know so far is that the rate of change of the volume, or dV dt, is equal to 6 meters cubed, or 6 cubic meters per minute. And we have to find the rate of change of the length. So we have to find dL dt. And we're going to do so when the volume is equal to 64. Okay, so if we take a look in here, we have to use our volume to actually find the length, because watch what happens if I just take the derivative of both sides. I'd have dV dt equals 3L squared dL dt. And while I know dV dt, that's right here, and I can plug that in, we're being asked to find dL dt, right? And then the great unknown in this problem, the thing that's going to cause us to pause, is that length. Right? If I don't know the length, then I can't solve for dL dt. So what you're going to do is take your formula for volume, because we're given that volume is 64 cubic meters. So set 64 equal to L cubed, and we need to take the cube root. So the cube root of L cubed will give us L, and that's equal to 4. Okay, so come back over to your derivative and plug in everything that you know now. So dV dt, the rate of change of the volume with respect to time, is 6. We've got 3. Now we're going to, in for L squared, we're going to be putting 4 in for L. So we're going to take 4 and square it. And then we have dL dt. So we have 6 is equal to 3 times 16. dL dt. 16 times 3 is 48. And then just keep solving it. So take and divide by 48. So you have 6 over 48 equals dL dt. 6/48 reduces to 1/8. I did say you could write your answers as decimals, so as a decimal it's 0.125, and it's the rate of change of the length, so the length would be in meters, and then it's respect to our time, which is in minutes. So the LDT, it's increasing, it's getting longer by a rate of 1/8 of a meter per minute. Okay, that's it for today, and we're going to be taking a look at some practice problems over the next couple of days.